Hey everyone, Kyle Shevlin from Portland, Oregon here to introduce you to my course, Data Structures and Algorithms in JavaScript for Egghead. Whether you studied computer science in the past and need a refresher, or you're like me and never had the fortune of studying computer science in school, my hope is that this course serves as a great introduction to the concepts of data structures and algorithms. During this course, you'll cover queues, stacks, linked lists, graphs, and trees, as well as breadth first and depth first search, tree traversal algorithms, and a variety of sorting algorithms. Now, the goal of this course is not to learn how to write these data structures and algorithms from scratch, even though that's precisely what we'll do. No, the real goal of this course is to get you to think differently. It's to get you to think about data structures. It's to get you to think about breaking problems down into their atomic and algorithmic steps. It's even about getting you to think divergently, about being able to come up with multiple solutions to the same problem and understand the trade-offs made in each solution. Learning these skills will help you in a variety of ways. It'll not only help you get through those nasty technical interviews, it'll also help you in your day job. It'll give you the skills you need to pick the right tool for the job and also to understand and be confident in the trade-offs you're making in your software. That said, please feel free to reach out and ask me any questions that you might have about this course. You can do so by leaving a comment on the lesson, or you can hit me up on Twitter. I'll put my handle on the screen now. Thank you so much for watching this course. To create our queue data structure, we're going to use a factory function that returns our queue as a plain JavaScript object. A queue is a collection of items that obeys the principle of first in, first out. When we place an item into the queue, we can only get it out after all the other items that have been added before it have been removed. Our queue will have several methods and properties: an add or enqueue method, a remove or dequeue method, a peek method to look at what's next to be removed, a length property, and lastly, an isEmpty method. In order to store our items, we'll use an array held in closure. Let's start with our enqueue method. We want to keep our collection in the correct order, so we always want to add to the array from one side of it and remove items from the other. We'll add items to the front of our array for enqueue with the array_unshift method. Next, we'll create our dequeue method using array.pop to remove the final item from the array. This ensures we maintain order in our queue, and every good queue is orderly. Next, we'll create our peek method that will return the item that's next to be removed. Now we'll create our length property. We need to use a getter for this. If we just associate queue.length with our length key, we'll get the value 0 because that's the value of queue.length when our object is created. Instead, we want to use a getter function that always returns us the current queue's length. Lastly, let's create our isEmpty method. Now we can try our queue out. A great use for a queue is a plan. A plan is a collection of steps that needs to happen in a particular order, so let's use a queue to make our plan. We'll create our queue, and just for good measure, let's test out our isEmpty method right away. When we log it out in the terminal, we see that it's true. Our queue is empty. Let's add a few items to our queue. How about make an egghead lesson, help others learn, and be happy? Now, if we peek into our queue, we should see make an egghead lesson. Yep. That works. Now, I've made the lesson, you're watching it, so let's dequeue it. And if we peek again, we should say, help others learn. Since I'm almost done with the lesson and I've taught you how to build a queue, I think I've helped you learn, so let's dequeue that as well. If we peek one more time, it says, be happy, and I think we're all happy that we learned how to make a queue. So let's dequeue that and then verify that our queue is empty. We can easily make a priority queue by using two queues, a high priority queue and a low priority queue together. Our API will be the same as a normal queue. We'll have an enqueue, dequeue, peek, and isEmpty method, as well as a length property, but we'll make some modifications. First, we'll create two queues that we store in closure, a low priority queue and a high priority queue. Next, our enqueue method receives a second argument to indicate that an item is high priority. We'll set it to false by default. If an item is deemed high priority, we put it in the high priority queue, otherwise it goes into the low priority queue. And we'll use a ternary to determine which priority queue it should go into. Next, Our dequeue method will make sure that the high priority queue is empty before it dequeues from the low priority queue. This ensures that all high priority items are dequeued first. This time we'll use an if statement to early return from the high priority queue or otherwise return from the low priority queue. Next, our peak method gets a similar change. Just like we dequeue from the high priority queue first, we're going to peak from the high priority queue first as well. In fact, I can copy paste this code and just make a change to which method is being called. Next, our length property is the addition of each queue's length property. Lastly, our isEmpty method is the conjunction of the two queues' isEmpty methods. Now that we've built our priority queue, let's try it out. Let's imagine your manager has given you a few tasks, a fix here, a bug there, and a new feature to build here. If we take a peek at our queue as it currently is, the item we should get back is a fix here. Great, that's working as we expect. That fix here was pretty easy. Let's dequeue it and make sure that's worked as well. Great, we dequeued a fix here, and now we're on a bug there. But let's say our manager comes to us with an emergency task, a task that needs to be done right away. And normally we couldn't put something at the front of our queue. It has to wait in line like every other task. But using the second argument in our enqueue method, we can put it to the front of the task we need to do. If I save this and we take a peek at our queue now, that emergency task should be what comes up. Let's say we've averted the crisis, we've solved our emergency task, and we're going to dequeue it. Let's make sure that's what we get back when we dequeue and see that we're back to a bug there being the thing we need to fix. Great, we dequeued the emergency task and a bug there is what we need to do. On with our tasks for the rest of the day. To create our stack data structure, we're going to use a factory function that returns our stack as a plain JavaScript object. A stack is a collection of items that obeys the principle of last in, first out. When we place a new item onto the stack, we have to remove it first before we get to any other item in the stack that's there before. This data structure is used for handling things like nested function calls in JavaScript, hence why it's called a call stack. Our stack will have several methods and properties. Push, pop, peek to look at what's next to be removed, length, and isEmpty. We'll start by creating an array held enclosure to store our items. We want to keep our collection in the correct order, so we always want to add and remove items from the same side of the array. We'll use the end of our array to make this happen, and thus we'll use the array methods that match our stack methods, push and pop, to do this. Using push, we place new items at the end of the array. Now with pop, we remove the final item from the array. This ensures we maintain order in our stack. Now we'll create our peek method by returning the last item in our array. Now we can create a length property. In order to do this, we need to use a getter function. If we simply call .length on our stack, we'll get the value 0 every time because that's the length of the array when this object is created. Using a getter always ensures we get the current array's length. Lastly, we'll add the isEmpty method to quickly tell if our stack has any items left in it. Now that we have a stack, we can try it out. A strange but everyday example of a stack is the act of getting dressed. We have to put clothing on in a particular order, and in order to change what we wear, we typically have to remove them in the reverse order. Let's create a lower body stack for the clothing we put on our lower body. We could create another stack for our upper body, but we'll save that for another time. I don't know about you, but the first thing I put on when getting dressed is some underwear, followed by socks. Then I throw on my pants, followed lastly by my shoes. If we take a peek at a lower body stack, we should see that shoes is the first thing we need to remove. Great. Let's say it's time to get ready for bed. I need to pop my shoes off, so let's do that. Now that we've taken our shoes off, if we take a peek at our stack, it should say pants are what comes next. And it does. Great. So let's pop those off as well and check the length of our stack. Looks like we have 2 items left to remove, but to keep this PG, I'll save the disrobing for a time when I'm not doing an egghead lesson. At least we know our stack works the way it should. A linked list is a collection of items where each item has a connection to the next item in the list, hence the word linked in the name. To make our linked list, we first want to create a node object for each item in our list. Our node has 2 properties, the value stored at this node and a next property which gets pointed to the next item in our list. This property defaults to null. Next, we want to make our list data structure. Our list will have several properties we want to keep track of: a head property, a tail property, and a length property. And we'll also want to create several methods for our list: push, pop, get, delete, and isEmpty. Our head and tail will both start as null, and our length will start as 0. We can also implement the isEmpty method pretty quickly, as it just returns whether or not the length is 0. Now we want to add our push method. When we want to push a value onto our list, we need to first turn that value into a node using our createNodeFactory function. Push places a new node at the end of our list, but depending on the length of our list, we might need to take somewhat different actions in order to achieve this. No matter what state our list is in, we know that eventually we need to update our tail property to this node that we've just created. We also know that we will need to increment our length property, so let's write that. Now, if our list does not have a head, that is the first item in the list, then we can also deduce that it doesn't have a tail, the last item in its list, because the list is empty. The opposite is also true. If our list has a head, then we know that it has a tail as well, because even a list of length 1 has a head and a tail. So if we don't currently have a head, our list head property is set to our new node. Since we didn't have a head, we also don't have a tail, and that needs to be set to this node as well. Since this is a special case, we can increment the length here and return the node now. However, in scenarios where our list does have a length and thus has a head and a tail, our new node gets set to our current tail's next property, and then we reset the tail like I said, and we increment the length. So the only thing we have left is to return the node. Now we'll move on to our pop method. Things get a bit more complicated here. We need to reason out a few scenarios. How do we pop items when our list is empty, when our list has a length of 1, and when our list has many items? An empty list is easy. If there's nothing to pop, we'll just return null. Now for our remaining scenarios, a list of length 1 and a list of a length greater than 1, we're always going to return the tail node, so let's store that in a variable. A list of length 1 means that our head and our tail are the same node, which means in order to pop this node off of our list, we also need to set our head and tail back to null. When we do this, we also need to reset our length to 0, but given that our length is 1, we can just decrement it. And then we return the node that we've stored. Now, for all other scenarios, we need to set the item before our tail, the penultimate item, as the new tail with its next value set to null. How do we do this? This is one of the inefficiencies of linked lists. Whenever we have to find an item, we have to start at the head and continue to call next until we find that item. For our case, we're going to start by having a variable called current that we're going to set to the head. Then we're going to create a variable penultimate that will eventually set to the penultimate item. Now, while we have a current node, we need to check if that current's next property is equal to the tail. That's how we know we have our penultimate item. And then we want to break our loop once we have our penultimate item. Otherwise, if we're not at that penultimate item, we set the variable current to the current.next property to move on. At this point, we should have our penultimate item, the one before the tail. We need to set its next property to null because it's going to become our tail. Now, because we're going to return a node, we need to decrement the length. And now we can return the node we stored before. Now we can move on to our get method. Our get method receives an index as an argument. If the index is less than 0 or greater than our length minus 1, then we know that the index is outside the range of our list and we can return null. If our index happens to be 0, we can just return the head. But for other scenarios, it's going to take considerably longer to get to the item in our list because just like in our pop method, we're going to have to loop through each item calling next on each one until we find the one we're looking for. So similar to before, I'm going to create a variable current that will start by setting it to the head. We're also going to keep track of an iterator because when that iterator matches the index passed in, we know we've gotten to the item that we need to retrieve. And we can use a while loop again to go through each of our items. Each loop through, we increment our iterator and we set the current value to the next value. Once our loop is done and we've gotten to the right index, we know we have the right item, so we can just return what current is currently set to. Now we can implement delete, which is very similar to get. The delete method also receives an index as an argument, and just like get, If our index is less than 0 or it's greater than our length minus 1, we're just going to return null. Now, if index equals 0, we're going to return the head of our list. But because I need to make some small modifications, I'm going to store it in a variable. We need to reset the head of our list to be the next item of our current head. We also need to decrement the length of our list. And in this scenario, we can return our deleted node right away. In all other scenarios, similar to the pop method and the get method, we're going to have to start from the beginning of our list and loop through each item until we find the item that we need to delete. I'll create a current variable and set it to the head, but I'll also need to store a previous node. We do this because a deletion in a linked list is simply taking a previous's next property and pointing it to the current node's next property, effectively slicing out the current node from the list. We also need to store an iterator to check against the index passed in to make sure we've gotten to the correct node. We'll use a while loop just like we did in the get method. We need to increment our iterator. We'll set the previous value to the current value and our current value to the current's next property. When our while loop is complete, we know that our current value is the value that we're going to delete. So I'm going to store that in a variable. Now we do the work of setting our previous's next property to our current's next property. This slices out the deleted node. Now we need to handle the case where we've deleted the tail of our list. If the previous's next value is equal to null, then we're going to set the tail to previous. Because we've now effectively deleted our node, we need to decrement the length. And finally, we return our deleted node. Now, I actually want to add one more method really quickly to our list. I want to add a print method so we can visualize it. For our print method, we'll create an array of values. And just like all the other loops that we've done in our linked list, we'll need to start at the head and loop through. So I'll store a current variable set to the head. And while we have a current item, we're going to push its value into our values array. Then we'll set our current variable to our current's next property. When this loop is done, we know we've gone through our entire list. So we're going to call join on our values array. We're going to pass in an arrow symbol that'll return us a string that looks like our values are linked together. Now that we've created our linked list, let's actually try it out. I'm going to create some values and we're going to push them onto our new list. Now let's verify that our linked list is not empty. It came back false because our list is full of items. Now let's pop off the last item in our list and see that we get E back. We can verify that after E was popped, that our tail is now set to D. Let's try our get method on the item at index 1. We could see that we got the node with the value B, which was the second value we passed in, which would be the first index. And we can see all the connected nodes to B. Instead of getting it, let's delete it and then look at our list. We'll do this by printing out our list. We see when we called delete that we got back that same node that we called with get. And then when we print it out, we see that we only have 3 nodes remaining and the values A is connected to C, which is connected to D. And this is a linked list. There are some modifications that you can make. There are doubly linked lists where each node also points to the node previous to it. And there's also lists that are cyclical in which the tail points to the head. But I leave these to you to work out on your own and try and make them yourself. A graph is a collection made up of nodes, also known as vertices, that may or may not be connected to other nodes. These connections are called edges. To build our graph, we're going to start by creating our node factory function. When we create a node, we need to give it a value that we can use to identify it. We'll call it a key. We'll describe adjacent nodes in our graph as neighbors, as there is no hierarchy implied by the data structure. Lastly, we need a way to add neighbors to our node, so we'll add an addNeighbor method that pushes a node into our neighbors array. Now we can create our graph factory function. createGraph receives an argument, directed. A directed graph's edges point in one particular direction, from one node to another. In order for 2 nodes to have symmetric edges, they must both point to each other. In an undirected graph, we assume the symmetry of edges. We'll set directed to false by default, and we'll return it in the object created by our factory function. Now, a graph is a collection of nodes and a collection of edges, so we'll create arrays for both of them in Clojure. We'll pass these references to our returned object as well. Now we'll start adding methods to our graph. The first will be the addNode method. addNode receives a key as an argument and uses our createNode function to add a node to the nodes array. We also want to be able to get nodes from our graph, so we'll add a getNode method. getNode will search for a matching key and return the first one, so we'll use arraysFind method to accomplish this. Next, we need to be able to add edges between nodes, so we'll create an addEdge method. addEdge receives two arguments, a key for the first node and a key for the second node. We'll use our getNode method to get those two nodes. We then will add node 2 as a neighbor to node 1. This happens regardless of whether the graph is directed or undirected. The same goes for pushing our edge into the edges array. We'll simply pass a string of our two keys, adding a delimiter between them. Now, if the graph is undirected, we also want to add node 1 as a neighbor of node 2. We're not going to worry about adding a second edge because we don't want the number of edges in our graph to be misrepresented. If we were to add an edge here, we'd have to implement a way of resolving both edges as one were we ever to count them and provide an edge's length property. Now that we can add nodes and edges, we'd probably like to be able to visualize our graph. We'll create a print method that will print out our nodes and neighbors in the console. We want to return a string derived from our nodes, so I'm going to map over our nodes, gather some data about them, and return a result. We'll start by destructuring the key and neighbors from each node. The string we're going to return will always start with the key. Now, if there are any neighbors, we want to map over each one of them and concatenate that neighbor's key into our result. Once that's done, we can return the result, and we'll call a join with a new line on our array of strings. Now we can create a graph and try it out. I'm going to create a directed graph of the Shevlin family, me, my wife, and our two cats, Krios and Tally. This graph will describe who loves whom in this household. Now, my wife and I love each other very much, so we can add an edge between us going in both directions. And we love our cats. Her a tad more than me, I'm more of a dog person, but we have no way of weighting our edges in this graph. So instead, we'll just add edges from me to both our cats and from Anna to both our cats. Next, our cats have very little love for each other. They tolerate one another, but they do fight from time to time, so we won't put any edges there. But Krios does love Anna, and Tally shows some affection towards me, so we'll add edges there. Now if we call the print method on our graph and run it in the terminal, we should see a printout of my family's relationships. As the name implies, breadth first search is a graph search algorithm that starts at one node and explores as widely as possible before going further down adjacent nodes. We'll add a breadth first search method to our graph object. We want to accept two arguments, a starting node key to find which node in our graph to start from, and a visit function to call when we visit each node. The first thing we need to do is get the starting node using the getNode method. Next, we need to keep track of which nodes we have visited and which ones we haven't. There are several ways we can do this. I'm going to do it through using an object. I'm going to reduce our nodes down to an object where each key is the current node's key and the value is set to false, that I can set to true later on when we visited that corresponding node. Next, we'll need to keep track, in order, which nodes that we need to visit. We'll use a createQueue function I've imported from another lesson. And the first node we need to visit is our starting node, so we'll enqueue it. Now, while the queue is not empty, we want to perform our search algorithm. Part of our algorithm will enqueue more nodes, and so this will continue to go on until we've visited every node in our graph. Now, each time we run through this loop, we want to dequeue the first item out of our queue and set that as the current node. If we haven't visited this node before, we need to call our visit function on it and set its corresponding value to true in our visited hash. Now, we want to loop through each neighbor of our current node, and if we haven't visited before, we want to add it to our queue. Now that we've implemented breadth-first search, let's try it out on a graph. I've pre-made a graph for us that I'll copy-paste the code into our file, and it looks like this. I want to use breadth-first search to print out the node keys as we arrive at each one into the console. I'll start from node A. If I bring the graph back onto the screen and we compare it to the result in the terminal, we can see how we branched out from node A and visited all of its neighbors before proceeding down node B's neighbors. As the name implies, depth-first search is a graph search algorithm that explores as far as it can down a particular path before climbing back up and working down another one. We'll add a depth-first search method to our graph object. This method will receive two arguments, a starting node key to find which node in the graph to start the search from, and a visiting function to be called as we visit each node for the first time. First, we need to get the starting node by using the getNode method. Next, we need to keep track of which nodes we have visited and which ones we haven't. There are several ways we can do this, but I'm going to do it by keeping a visited object, where each key corresponds with a node's key and the value starts as false. Now, depth-first search involves a recursive algorithm. Essentially, if there's another level to go down, we need to explore that one until we reach a dead end. I'm going to create an explore function that we will call on our nodes. If we visited this node, then return from the function immediately. Otherwise, call the visiting function on the node and mark it as visited. Next, we want to loop through each of this node's neighbors and call explore on them. Lastly, we start our algorithm by calling explore on our starting node. Now that we've created our depth-first search algorithm, let's use it. I've pre-made a graph that I'll copy-paste into the file that looks like this. I want to call depth-first search on our graph, starting at node A and logging out each key as we go. If I bring the graph back onto the screen and we call our search in the terminal, we could see that we went as far down the path of A we could before we climbed back up and went down another path. A tree is a graph without any cycles. A cycle is when three or more nodes are connected in a circuitous path. Tree nodes, instead of having neighbors and no hierarchy like a graph, might be thought of having children and are hierarchical. Each node can contain many children. No children may have an edge between them, and they may not be connected to any other parent node. To write our tree data structure, we'll start by creating a function to create our nodes. Each node receives a key as an argument. We'll return that key in the object returned by the factory function. Next, a tree node can have many children, so we'll create an array and return that reference. Lastly, we'll add a method called addChild so that we can add children to this node. addChild will receive a key as an argument, create the node, push it to the children array, and return that node. Now we can create our tree factory function. Trees must have a root node, so we'll expect the root key to be passed as an argument when the tree is created. We'll use this key to create a node and we'll assign it to root and return it in our tree object. This tiny object is all we need to begin to use our tree, since each node contains in it the ability to add nodes to it. Perhaps the most common tree structure web developers deal with on a regular basis is the DOM tree. The HTML of every page on the web is a tree structure. We can create the basic layout of a page pretty quickly with our tree. I'll create a tree and name it DOM, giving it the root key of HTML. Our HTML node adds two children, head and body. Our head node receives one child, our title. Our body node likely has many elements. In our case, we'll give it a header, a main, and footer. Our header probably has an H1. Our main perhaps has a paragraph. And our footer might have the copyright year. Now that we have our tree structure, it might be nice to visualize it. Let's create a print method that traverses our tree and logs out each node's key. I want to return a string from our print method, and I'll be concatenating onto this string with each level we traverse through our tree. So I'm going to create a variable called result, and I will return that. I'm going to create a traverse function that we'll call recursively on our nodes. Traverse will accept 3 arguments: the node it's operating on, a visiting function to fire on each node, and a depth argument I'm going to use for my output. Depth isn't necessary in this implementation and could be derived from the data, but this will be useful for the lesson. Now, we start by visiting our current node. Then, if the node has any children, we want to traverse through each one of them, passing the same visiting function, but increasing the depth by 1. Now I'll create a function to pass as our visiting function. This function will mutate our result string. For the very first node key, I only want to return the key. But for every subsequent key, I want to create a new line and then add twice as many spaces as the depth before each node key. This will give a nice nested layout to our output. Next, I want to traverse starting from the root node and passing our visiting function and a depth of 1. Now that our print method is complete, let's call it on the DOM tree we created before. Need to create a little more room in our terminal so we can see the full visualization. And there you can see our DOM tree printed out. Binary trees are trees whose nodes can only have up to 2 children, hence the word binary. We'll use a function to create our binary node object. A binary node receives a key as an argument and has a left and right property set to null. It also has the methods addLeft and addRight. AddLeft and addRight both receive a key. We create a new node from that key, and we update the left and right properties respectively, and then we return the new node. Now we can create our binary tree factory function. Since trees must have a root, our function receives a root key as an argument, and we can then create the root node using our node factory function, and we pass this to the object we return from the function. Now, binary trees have 3 specific types of traversals: in order, pre-order, and post-order. I'm actually going to turn these traversals into an enumerable. Each item in our enumerable will represent the corresponding traversal type, and the value for each item will be a function that we can use to traverse our tree with. Each of these traversals is quite similar. They each have the same function signature, they receive a node and a visiting function, and because these are called recursively, they each have the same guard statement. We only want to operate if we know that the node is not null. We'll start with in-order traversal. In-order traversal starts by going as far down the left branch as possible, then visiting our current node, and then going down the right branch. The way we do this is to call our traversals in order function recursively, like so. Pre-order traversal is very similar, but we change the order in which we visit our nodes, and we change which traversal method we're using to traverse those nodes. I'm going to copy paste the code from the in-order method to the pre-order method and make those changes. If pre-order means that we visit our current node first, then it makes sense that post-order traversal means we visit our current node last. So allow me to copy paste again and make those changes. Now that we have our traversal methods, let's add a print method to our tree so that we can use these different traversals and see their output. We'll pass a traversal type as an argument into our print method, but we'll default that value to in order since it's the most common traversal. We'll keep our print method pretty simple. We want to return a string, so we'll start by creating a result variable set to an empty string. Now we'll create a visiting function that when it visits each node, it'll concatenate the key onto our result string. We'll add a little touch where if there is no length in the current result, we only return the key. Otherwise, we'll attach a delimiter to our key. Now we can use the traversal type passed in on our traversals enumerable to get the right method to be used. Finally, we'll return our result. Now that we have our print method, let's try it out on a tree. I'm going to copy paste some code in here to make a tree that looks like this. As you can see, our tree is a collection of letters from the alphabet. Why don't we try calling the print method on our tree and logging out the results with our different types of traversals? We'll start with the in-order traversal. And if you remember, we defaulted it to in order so we don't have to pass in an argument. As you can see, we went all the way down to our leftmost node, the H node, and then we began to work our way back up. It's why the A node comes in the middle, because we visited that before we then traversed down the right side of our tree. Let's change our traversal type to preorder and see the difference. As you can see with preorder, the first node we printed is the first node we visited, the A node. We then went down the left side of the tree, going all the way down B, D, and H, going down each left branch before coming back and then going down the right branches. Now let's do our last traversal type and do post order and see that difference. As you can see, we went all the way down the leftmost branch getting to the H node again, but we also went all the way down the right branch before we visited our current node A, which comes last. To write the bubble sort algorithm, let's create a function that accepts an array, mutates that array for sorting, and then returns that array. Bubble sort works by looping over the array as many times as necessary to get it sorted. Each time we iterate over the array, we check if the current item is greater than the next item. If it is, we swap it in place and we indicate that we've made a swap during this iteration. Then, if we've made a swap, we loop through the array again. We continue looping until we make a pass where no items have been swapped. Since the way we know that an array is sorted is that no swaps occurred during it, we need to at least iterate over the array once in order to determine that it's sorted. This is a perfect situation for a do-while loop in our algorithm. Since the condition we're going to test is whether or not a swap occurred in each iteration, we need to store a variable that holds that swapped state for us, and we can pass it as the condition into our while portion of our do-while loop. Now, the first thing we need to do in our do block is reset the swapped value. This prevents any bugs from occurring from setting swap to true in the previous iteration and forgetting to reset it. Now, we want to iterate over each item in our array, so we'll use array.forEach for that. ForEach receives a callback function, and the arguments given to that callback function that we need are the item and the index of that item. The condition we're checking is if this item is greater than the next item, so we can use array index plus 1. If this condition is met, what we want to do is temporarily store our current item in a variable. We'll then set the current array index to the next item and set the next array index to our temporarily stored item. This has swapped our two items, and thus we can now set swap to true. And that's our bubble sort algorithm in total. But I want to add something that helps us visualize what the algorithm does through each iteration. So I'm going to use the print array utility that I've imported into this file to display the state of the array before each comparison. Now I'm going to create an array of unsorted numbers, and we can pass that numbers array into our bubble sort function. If I log this into our terminal, we'll get to see the array as it transforms through each comparison and swap. If we scroll all the way up, we can see how our array was sorted. Now this was happening before each comparison. The 10 quickly moved all the way to the right because it's greater than every current item. And we begin to see less drastic movements of items as the array becomes more and more sorted. All the way until we get to the end and we see what appears to be about 19 redundant passes through the array. This happens because the 2 swaps with the 1 in the very last iteration here. And then we go through all the rest of the iterations, the 9 iterations of our array, with swapped being true, and then we need to make one more pass through the array even though we know it's sorted because we need to guarantee that nothing gets swapped. To create our insertion sort algorithm, we'll create a function that accepts an array, sorts it, and then returns it. Insertion sort works by using a nested loop. We'll take the first item in the list and assume we have a sorted list of length 1. We'll then compare the next item to it and place it before or after it depending on which item is greater. Since we'll have 2 loops going, we need to create 2 iteration variables. We'll use I and j. Next, our outer loop will start at the second element in the array, thus I will start at the value of 1. This loop will loop through the entire length of the array from the second item, so we can use I as less than array.length, and we can increment I. We'll have an inner loop that starts at the first item in our list, so j will start at 0, But we only want to loop up to the current item being iterated over in our outer loop, so our second statement in this is j is less than I. And here we want to increment j. Remember, this inner loop will reset each time our outer loop advances to the next number. What we want to do inside our two loops is compare the item at array index I to array index j. If item I is less than item j, then we want to move the item I to the position of item j. I'm going to use array destructuring to get an item variable, and I'm going to use the splice method to get it. We want to splice at the index of I, and we want to only get one item deleted and given back to us. I'm going to use the splice method again to insert that item at the j position. That's the insertion sort algorithm, but we want to be able to visualize it, so I'm going to use the print array utility method I've brought into the file in order to print each time we make a comparison. I want to add one more print array just before we return the array. This way we'll get to see the array in its final sorted form. Now that I have that, I can create an array of unsorted numbers and pass those numbers to our insertion sort function. If I save that and print that to the terminal, we can examine how the algorithm worked through each iteration. If we scroll up, we could see how 10 moved one spot during the first one, a few more spots each time afterwards. And what this kind of reveals to us is how the inner loop of j was comparing more numbers each time I got a little bit bigger. Eventually we could see 10s moved all the way to the right, and that our list is sorted and organized. Merge sort is a recursive sorting algorithm. If you don't understand recursion, I recommend finding a resource to learn it, but in brief, recursion is the act of a function calling itself. Thus, merge sort is accomplished by the algorithm calling itself to provide a solution. Merge sort divides the given array into two halves, a left half and a right half. And we call merge sort on these subarrays. We continue to split our subarrays until we get arrays whose length is less than 2. We then begin to stitch our small arrays back together, sorting them on the way up. This is an efficient algorithm because we start by sorting very small arrays, and by the time we reach our larger ones, they are already mostly sorted, saving us the need for expensive loops. To create our algorithm, we'll actually need two functions, our merge sort function and a merge function that does the combining and sorting of our subarrays. Merge sort receives an array as an argument. Since this function will be called recursively, we want to start with our base case scenario. That is, the scenario in which we want to return right away rather than call it recursively. In our case, if the array we receive has a length that's less than 2, we just need to return that array. There's no further splitting that we need to do. Otherwise, if the array is longer than 2, we need to divide it into left and right halves. I'm going to do that by finding the middle using math.floor and dividing the array length by 2. This will give me an index I can use to divide the array into two subarrays. We'll create our left array by using slice from 0 to middle, and we'll create our right array by using slice starting at the middle. Now that we have our left and right subarrays, as I explained before, what we're going to do is return a merged function that's calling merge sort on the left half and the right half. Now that we have our merge sort function created, we need to create the merging function that will actually take our two subarrays and sort them out and stitch them back together. Our merge function needs an array that we can store our sorted items into, so we'll create that first. Now what we want to do is compare the first items in both the left and the right arrays. If the left item is less, we push that into our sorted array. If the right item is less, we push that into our sorted array. Since we're comparing these items and stashing them into the sorted array, we actually want to remove them from the left and the right arrays. So in this case, since we're pulling from the beginning, we'll use the shift method. Now, as we're doing this, we're changing the length of our arrays. We only want to compare them when we know that we have values in both arrays, so we should do this during a while loop that makes sure that we have length in both arrays. Now we need to consider a situation in which we've depleted the left or the right array, but there are still items in the remaining array. So what we want to do is we want to stitch together our sorted results and then place the remaining items in either the left or the right into a new array and return that. I'm going to call this array results, and we'll use the spread operator to spread our sorted array, then the left array, and the right array. If the left or the right array is empty, it'll spread nothing, and then if the other one still has items, it'll just spread the remaining items into it. To add some interest to this as we watch the algorithm take place, I'm going to actually log out the results for each merge. Now that we have our merge sort function completed, let's create an array of unsorted numbers and call merge sort on them. Let's try logging out the results of our merge sort. And you can see one stack merged 5 and 10, the next 7 and 8, the next put 4, 7, and 8 in the right places, then 4, 5, 7, 8, and 10 as it merged those all together. And then we got to the right half of our array. We had 1 and 2 got sorted, which were 2 and 1. 6 and 9 got sorted, then 3, 6, 9, then 1, 2, 3, 6, 9, and then we combine our two lengths of 5 together to end up with our sorted array 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Quicksort is a recursive sorting algorithm. We take our original array, breaking it down into smaller arrays to sort, calling quicksort again on these smaller arrays. In particular, quicksort uses the concept of a pivot. We pick one item, it could be at the head or the tail or somewhere in the array, so long as it's consistent, and then we compare each item to that pivot. If it's less than the pivot, we're going to push it into a left array. If it's more than the pivot, we're going to push it into a right array. We then call quicksort on those sub-arrays, merging them together, returning the array that's the result of quicksort on the left, the pivot, and quicksort on the right. We'll make a function quicksort to create our algorithm. Quicksort receives an array as an argument and will return an array as well. In this algorithm, we'll return a new array of sorted items, so for now, we'll return an empty array. Next, since we know we will call quicksort recursively, we need to establish our base case to prevent a stack overflow. If the array length is less than 2, we want to return that array. Now that we've finished our base case, what we want to do is establish our pivot. We'll use the last item in the array as our pivot, and since I'll need the pivot index later in the algorithm, I'm going to store that as a variable and derive the pivot from that. I'll also create empty arrays for our left and right subarrays. We're going to push items into these arrays in just a moment. Now we'll create a for loop that will iterate through every item in the array up to the pivot, hence why we stored the pivot index. For each item in our loop, we want to compare that current item to our pivot item. So I'm going to store our current item as a variable. Now, if the current item is less than the pivot, we'll push it into the left array, otherwise we'll push it into the right array. With our loop done, we now want to call quicksort recursively on our left and right arrays, placing our pivot in the middle. Now that we've finished our algorithm, I want to add a way to visualize what's going on within it. So I'm going to use the print array utility that I've imported at the top of this file and place it inside of quicksort. Now that we can visualize what's taking place in our algorithm, let's create an array of unsorted numbers and pass that to quicksort. We'll save that and log it into our terminal and see what happens. Our first printout of the array is the complete unsorted array, and our pivot was 4 because it's the last item. So the first array we see called recursively is all the items less than 4. That's 3, 2, 1. The pivot was 1, and thus we got 3, 2. The pivot was 2, and we ended up with 3 as the final one because it was the only one we had available. The next subarray was everything left that was put into the right array, 10, 6, 7, 9, 8, 5. 5 is our pivot. Everything is greater than that, so that was put into another array, and it continues to break down. What this doesn't show us, though, is what our sorted array was. A quick way for us to fix this is to store our returned array as a variable and log out that returned array and just see that again. I'm going to call this one more time. And now we can see how it starts to stitch them back together. If we come back up, we see how they were divided, continue to be divided, and now that we get down to 10, we start to see them get stitched back up. You can even see that 4 wasn't used in any of these iterations until the very final one because it was the original pivot of our whole algorithm.